In this video, we'll be discussing centripetal acceleration and force. Just a little bit of background, we will be looking at objects that are moving in a circular motion. And while we haven't talked about circular motion yet, we have the skills in our toolbox to understand the forces acting on an object to cause it to go in a circular pattern. So we're going to take an object and we're just going to have it moving in a circle. This could be a car traveling around a track. This could be an object being swirled overhead, being hung onto by a string. There are a lot of different things we can that we know of that have circular motion. So as remember, by definition, acceleration is equal to the change in velocity over time. Acceleration is a vector, therefore we have to consider both the magnitude, or the size, and direction. In circular motion problems, something that's really nice is that we work with constant speed. So if we're working with constant speed, what is actually changing to provide that acceleration? Well, it's the direction. It's the whole point of circular motion. We're going to be constantly changing that direction, and that change of direction will provide us an acceleration. So let's look at a typical circular motion problem. Okay. So if we're going to take a circle and have an object move around it, there are four different, well, pretty much any point along the path that we can look at, but I'm going to look at these four positions. Okay. We're going to start at the top. So at the very top, we're going to have our object has a directional velocity like this. It's tangent to the circle. And as we spin around and we come down here, we see that our velocity down here is still tangent to the circle. We come around, again, we're spinning around, we have our velocity, once again, tangent to the circle. And over here, the velocity is still tangent to the circle. So in all four cases, the velocity is tangent to the circle. Remember, tangent's just a word in math class that means parallel to a point. Now we need to look at our acceleration. So as this object is traveling around in a circle, the velocity is constantly changing. And so without an acceleration providing that change in direction, where would this object fly off? It would go straight off. So which direction does it head in order to move down this path? The acceleration is actually trying to pull it in towards the circle, perpendicular to that velocity. Same thing down here. Without an acceleration, the object at this point would want to fly off this direction, tangent to that circular path. But because the acceleration is pulling it back towards the center, it swoops around and gets to this bottom point. Once again, without this inward seeking or center seeking acceleration, the velocity would fly off, in this case off your screen. We have this acceleration swoop us around to this point, and without that same acceleration, it would fly upwards. But because it has the center seeking acceleration, it swoops back around to the top. And this path continues over and over and over again. So the direction of the acceleration is always pointing towards the center. Okay. So your velocity will always be tangent to the circle, while your acceleration will point towards the center. Okay. And that brings us to what on earth centripetal means. I pretty much jumped in without explaining what centripetal means. In this case, or by definition, centripetal means center seeking. And that works out really well for this acceleration. It's pointing towards the center. So we are constantly seeking the center of the circle for our acceleration. We can write this as a neat little formula. To designate that this is centripetal acceleration, we put a little subscript C next to the A. Okay? That tells all of your readers of your problems that you're looking for your centripetal acceleration. Now, our centripetal acceleration is going to be equal to v squared over r. If you'd like to see the derivation of this, please come see me outside of class. It's not something too difficult to understand. It just takes a little bit of time. So v is still velocity, and r is our radius. Okay, the radius of your circle. Okay. And that is centripetal acceleration. But we know that whenever an object is accelerated, there has to be a net force. That's according to Newton's second law. If there's an acceleration, there has to be a net force. Okay? This is called the centripetal force. Okay? And we abbreviate this as F with a subscript of C. Now, this was not on our original list of forces that we talked about at the beginning of this unit. So here are a couple of examples where our centripetal force can come into play. If a mass is twirled in a circle at the end of a string, the acting centripetal force is just tension. Okay? If a car is rounding a corner on a highway, what is actually keeping that car on the road is friction. And when the moon orbits the Earth, the force that's actually keeping the moon falling towards the Earth around in its orbit is gravity. Okay? So we summarize each of these three cases as F of C. It lets us distinguish between your normal tension, friction, and gravitational forces into something a little bit more specific called centripetal force. Once again, centripetal meaning center seeking. So it's a force that's trying to pull this object towards the center of its path. So using Newton's second law, which we know is F equals to mass times acceleration, we can relate the force due to the centripetal, and we can set that equal to a mass, whatever mass we're using, times our centripetal acceleration. Okay. If we want to substitute in our definition of centripetal acceleration, we can set this equal to mass times v squared over r, having that radius involved and the velocity. Okay. So a few examples of this, just so we're all on the same page. I have three here for us. The first one is a car traveling at 14 meters per second goes around an unbanked curve in the road that has a radius of 96 meters. And the question is, what is the centripetal acceleration? So there's a few good keywords here. The first is that we have two numbers. We have a velocity of 14 meters per second and a radius of 96 meters. We're looking for centripetal acceleration. We don't know what that is yet, but we know the units will be in meters per second. And the other key word here is unbanked. So unbanked is just another word for flat. It's a flat curve. We're not on a hill, or if you think of NASCAR racing, how they try to go up the bank, so they're essentially turning their car more vertical on its side than flat horizontal. We will not do banked curve problems. You have the tools to do it. They just take a lot longer than these unbanked curve problems. This is a very simple, straightforward question. We're just looking for AC, which by definition is v squared over r. And we have v and we have r, so it's just a matter of plugging in your numbers and calculating an answer. The most common thing people forget is that we are doing v squared. Sorry, I made a mistake there. So we do have to square that 14, then divide it by 96. Okay? And you should arrive at an answer of about 2.04 meters per second squared. That's as easy as these problems get, so we're going to take it up one step. In this problem, we still have a car. It's a 900 kilogram car moving 10 meters per second. It's taking a turn around a curve with a radius of 25 meters. This problem is asking us to determine the net force acting on the car. So let's look at what they give us. We have a mass, a velocity, and a radius. So your mass is 900. Velocity is 10 meters per second. And your radius is 25.0 meters. We're looking for F net, so we'll do this for now. F net equals something we don't know yet, but we do know that the units are newtons. Okay. So think about a car acting in a circle or moving in a circle. Which direction is this force going to be pointing? Well, we know our acceleration is towards the center, which means our force also has to be towards the center. So when we say F net for a moving, circular moving problem, it's the same thing as saying, what's F of C? What's that centripetal acceleration? So instead of setting this as simple to mass times acceleration, we can do mass times our centripetal acceleration. We can do a quick substitution because we know that our centripetal acceleration is v squared over r. And from there, I believe we have all the numbers we need. We have 900 times 10, don't forget to square it, divided by a radius of 25. And I got an answer of 3,600 newtons. Okay, that wasn't too bad either. So we're going to take it up one step further. And you're probably thinking, oh, Miss Alvord, this is too much. Well, this is probably as difficult as these problems will get. So I wanted to give you an example of it just so you could have it for your information. So here we have a 0.50 kilogram mass sitting on a frictionless table, and it's attached to a hanging weight. The 0.5 kilogram mass is whirled in a circle of radius 0.2 meters at 2.3 meters per second. Calculate FC. Okay. So this is our object. It's sitting on a table, and so the best way to imagine what's going on is think if there's a circle in the table, a hole there that there's a string coming out of, and this object would be actually swinging on top of the table in a circular fashion. So since we're dealing with forces, it's probably helpful to do a free body diagram. So let's do the bottom hanging mass yet. We don't know too much about it, but we do know that there's going to be a force of gravity. That's why it's a hanging mass, and a force of tension going up the string. For the box on the table, we know that there is still force of gravity, and we know that there is a normal force that is counteracting that gravitational force. And the force that's going to cause it to move around in the circle is the tension force. So recall what we were talking about with our tension forces. Our tension forces always cancel out. That'll come in handy in just a second, but before we get there, we're only looking at this particular mass for the moment. So what is the only force that's causing it to go in the circle? Or essentially, what are we looking for? We're looking for FC, and we know that in this case, it's just going to be the value of tension. Okay? That's very helpful for us to understand at this point in time. So let's see what information they gave us. We have a mass, 0.5 kilograms. We have a radius of 0.2 meters and a velocity of 2.3 meters per second. We know we're looking for FC. We know that the value or the unit is for newtons. So here we can just plug in Fc is mass times v squared over r. So there, all I did was I took mass times AC and then substituted in the formula for AC. From there, you just plug in your numbers. We have our mass, 0.5. Multiply it by your velocity, and don't forget to square, and then divide by your radius, which was 0.2. Be careful with all of these decimals plugging into a calculator. Shouldn't be too difficult, but a lot of mistakes are made when decimals are present. So I have a force of 13.23 newtons. And that would be your answer for this part of the problem. Okay? So we know that our centripetal force is just the tension. That's the only force that's going to cause it to move in a circle. And that's equal to mass times the centripetal acceleration. I substituted in the centripetal acceleration formula, and then I plugged in all of the information that they gave me and arrived at an answer. Now, that wasn't too hard, so what makes this problem difficult? Well, it's a two-step problem. The next part wants you to calculate the mass of the hanging weight. So we already have the free body diagram up here. So if we wanted to calculate the F net equation, we know that we are going to have tension and we're going to subtract F of G. Okay? This is a hanging weight, which means that it's just hanging there. There is no acceleration on this object. So that means our F net equation is equal to 0. Okay? What does that mean about our tension and gravitational forces? Well, they should be equal to each other. We can substitute in that we know Fg is equal to m times g. And so the question remains, what's m? We know g, but then what's t? Well, as we stated in the first part of the problem, our centripetal force is just the tension that's there. Recall that these tensions will be the same. The tension along every point in the rope is the same. So if this is the value we got for tension in part 1, that's the value we want to plug in for part 2. So after quick rearranging, we can simply say that the mass will be equal to the tension force, which we calculated in part A, divided by the 9.81 gravity we know, and we should be able to calculate a mass. See, I got 1.35 kilograms. If you got a slightly different number, it